let me go back up a little bit, Henry, please. We were thinking about these carboxylic acids, and other like dicarboxylic acids are shown here in the middle. And we were thinking about acid-base chemistry, and then going back down, trying to make the case to wow everyone that it was quite surprising that this position here, pointing to the left part, the alpha carbon, the one that's next to the carbonyl group, is relatively acidic. So an acetone deprotonation of this carbon has a pK of 19 compared to around 50 for just the propane that we have up on the top. So that's around 30 orders of magnitude difference. So, Lorianne, this lecture material here will not be on tomorrow's exam, unless we want it to be. I put it together, the exam already, but we could switch some questions out. Maybe not. So, no. Okay. Yeah, I think there's enough material. However, there will be one acid-based question. Okay. Every exam has to have at least one acid-based question. Kyle, I think I said yes. Yeah. No, I'm just kidding, actually. So actually, there's something not to joke about. So this material will not be on the exam tomorrow, except for one acid-based question. But hopefully this is useful, because I know maybe back when I was in college, I would have just tuned out. But we'll make this useful. This is really exciting stuff, actually. All right. So what we did is we saw that we can. James is excited. I'm sure it's the enolate chemistry. We can deprotonate here alpha to the carbonyl, and when we draw the conjugate base here, we wanted to come up with an explanation as to why this proton is quite energetically easy to remove, and it comes back to resonance stabilization. We could draw a resonance structure, and that's what we have down below, and we're introducing some new terminology, and this is known as an enolate ion. And this enolate chemistry will be all the rage for the next couple of weeks in the class. One of the things we'll see is that these compounds, these ketones, these carbonyl compounds, can exist oftentimes both as the ketone and the enol form. And these are known as tautomers. And these are constitutional isomers. I see it still says isomerase. That's the start of the biochemistry side of me coming out. But it's constitutional isomers that differ in a position of a hydrogen. And the key thing is that they're not resonance structures. So they're actually real different compounds that can convert. And these can be formed under both basic and acidic conditions. So let's first consider the basic conditions. And we can go through this to review some of the types of mechanisms that we've seen before. So let's just take acetone. And in the presence of hydroxide, and actually one thing that comes up when thinking about this as well, isn't the hydroxide just going to attack here? We've been talking all about this carbonyl chemistry, and now all of a sudden we're saying something different is happening. And I know that's kind of confusing, and the answer is actually yes. What's been happening in all of our reactions is that, say, this base could act as a nucleophile, attack here, like we saw in the beginning of our time together, but it can also take a proton off. And there's a lot of times different reactions going on behind the scenes, so that's important to realize. But what we can do is have this hydroxide act as a base. It's going to take a proton off. And let's write the resonance structure. So we'll just put the electrons directly right on that carbon. So these are all steps in equilibrium. We have this now negatively charged species. And we can write a resonance structure just like what we saw above. Negative charge now on the oxygen. And we have this here. And then we generated water. So we can regenerate our hydroxide by taking a proton off of water. To form this, plus hydroxide again. So this species here now, with the alkene on the far right here, the alkene alcohol, that's known as an enol, alkene alcohol. And this one here with the negative charge, this is known as an enolate, or often as the enolate ion. So notice, compared to our previous reactions, again, under basic conditions, negative formal charge is in the resonance hybrid, and then negative formal charge on the end. So it's probably not a surprise now if we go to thinking about the reaction under acidic conditions, probably going to be dealing with positive formal charges. So now let's start with acetone again. Now we have a little bit of acid around it. So hydronium, something like water and sulfuric acid. Now, just like what we saw with all of our other carbonyl compounds under acidic conditions, let's first protonate the carbonyl group. So very similar to what we've seen before. Put the lone pair in there. Now what this does is, like we've seen before, that this makes this carbon more electrophilic, which it does. But another thing this protonation actually does is it makes this proton more acidic because it's going to stabilize the intermediate. So we could have water pick up a proton here. Oops, I don't know what happened with that circle. Let's have water pick up the proton that we have here. And then let's move these electrons in here and then out onto this oxygen. Let's see what we get. So I have a double bond now. And let's see what am I doing here. Oh, actually, sorry, let me rewrite this a little bit differently. I skipped a step here. Sorry, I'm going to erase something here. Let's first, before we actually deprotonate, let's actually just write this resonance structure. So we have this protonated species, and what we could actually do is write this resonance structure. We'll move these electrons up onto this oxygen. This way it's parallel with our resonance structures. Oops, sorry. And so now what we're going to do is put the positive charge here on the carbon, which would really help then emphasize how this proton, this one here, this proton now is very acidic because it's next to that carbocation. So we'll show all the steps this one time. So then we can then take off this proton, which is going to form our enol again, plus we've regenerated our acid. So two reactions here under basic conditions on the top and under acidic conditions. And again, notice the formal charges, like we said, they're all negative on the top. On the bottom, we start with H3O+, positive formal charges in our resonance hybrid, and hydronium again. Now, these species here are tautomers. On the left, this is the keto form. In both of these cases, this is both acetone. And then, I guess I should have maybe stuck with green. This is the enol form. Write it again, purple, on both sides. And the relationship between these two compounds is that they have the same formula, but they have a hydrogen in a different place. So it has a hydrogen down here, and use the acidic conditions, or the hydrogen connected to the oxygen. So they would be constitutional isomers because they have the same formula, but a different connectivity. But unlike, this butane versus this, these two compounds, they don't interconvert. If you leave them in a flask and you mix, right, these two compounds are two different flasks, they're not going to convert between one and another. However, the keto and the enol form will interconvert under both acidic or basic conditions. So these are constitutional isomers that actually interconvert, and so they are known as tautomers. And then once again, the key thing is the relationship between the keto form and the enol form is they're not resonance structures. That's what I scribbled up here on the top, because they are real different compounds. Okay, so you'll hear the word tautomers and tautomerization. So the cation version here, this one, Angela asked, in enolates, the enolate will be the negatively charged species. This one we're not going to really see, this protonated species, because this would actually still be the keto species. So that's a good question, and this is the resonance hybrid of the keto species. So under the acidic conditions, you actually go from the keto form to still something that's keto-like to then the enol. So this would be we only have the enol form over here. What we're going to see is that many times the reactions use the actual enolate ion. So that one's going to be more important. So that one kind of stands out on its own. There's not really a parallel here for the acidic conditions. So that's a great question. Okay. So I had this more in the video. We're not going to spend much time to go over it, but a lot of these ketones exist in the keto form. So we've been drawing acetone here all along, and it exists 99% or more in the keto form, and very little in the enol form. However, there are some dicarbonyl compounds, as shown down below, that can exist a lot more in the enol form, and there's a couple of different reasons why one might see that. In this particular case, you can imagine having a hydrogen bond between this oxygen and this hydrogen, which would help stabilize the enol form, and that can actually have a pretty significant effect. And then on the right, notice this is phenol here that we on the right we've drawn. We could actually draw a tautomer that would look like this, and so this is actually an enol, the enol form of it here. So we have a OH and then a double bond next to it. However, phenol is predominantly this form and not the keto form, even though the keto forms are generally more stable because of the carbon-oxygen double bond is more stable relative to the carbon-carbon double bond. However, this is an aromatic compound, whereas this one on the left is not. This carbon is sp3 hybridized. And we spent all this time talking about how important aromaticity is in stabilization. So that's why phenol actually exists in the enol form. So I know we're going through this a little quickly, relatively quickly, but hopefully this is going to lay the foundation for some of the things discussed in the next couple of weeks. And it's not a whole lot of new material, but building on some of the things we've already seen. So at the outset, a lot of the reactions that'll be seen in the next couple of weeks is that you're going to generate the enol or the enolate form of a particular compound and then use that in the reaction. And this can be done under acidic conditions. And let's not redraw the mechanism, but acidically, you're going to use something like hydronium ion, and you'll have the mechanism that we saw above, and you're going to generate the enol form. And that's pretty much it in terms of the acidic conditions. Where the choices oftentimes have to be made are under basic conditions, and this is actually generating the enolate. Now here, below, I showed 3 methods here to generate an enolate, and for something like acetone as our example, they all look the same. However, we'll see shortly that there are some differences here. Now, one way to generate the enolate is to use what we'll call a weaker base, and this is ethoxide. There's a common one. Sorry, Kyle, I'll make it smaller so I can. Is that fine enough? So we're going to. Okay, excellent. So then, compared to the acidic conditions now, for the basic conditions, we'll have what we call a weaker base. And I say weaker because we've used ethoxide or hydroxide, OH minus, or methyl methoxide, for example, as a base. And the strong versus weak a lot of times depends on the comparison. But this is going to be weaker than the base that's shown here under letter B. So this base could be used to generate the enolate, just like what we saw before. And you can actually draw the other resonance structure where we take off the proton, and we can move the electrons all the way up to the oxygen if we wanted to. These are resonance structures. I'll draw it this one time again here. So we can draw this resonance structure. So there's our enolate and enolate ion that we generated with ethoxide. So we would have an equivalent of ethanol that we would make. Now, this idea of this weaker base is because there's a very commonly used base that's much stronger that's used in generating an enolate. And this is this compound here, which is lithium, diisopropyl amide, or LDA for short. So this is a great, strong base, and has a much higher pKa than the ethoxide, which is going to be around 16. It says a pKa around 32 for deprotonating to make the amide. So a very strong base. It has these 2 bulky isopropyl groups around it, basically surrounding the nitrogen, so it's okay for it to pull off a little proton, but it's preventing it to act as a nucleophile. So LDA will do the same thing in this case. It's going to pull the proton off. I want to make those electrons a little closer to the carbon. So here mechanistically it's the same idea. Same idea with the resonance structures. We could write so we generate our enolate ion, plus we'll have diisopropylamine, and lithium would be coordinating something to the negative charge. Now, what's important here is actually the weaker base above. This one will squeeze it in, actually as an equilibrium, deprotonating and protonating. And that's going to be important because this will come up later on to be it's a kinetic versus thermodynamic product. Whereas LDA is once that rips that proton off, the reaction is not going backwards. And so it's a way of essentially just generating in one direction, quantitatively or 100%, the enolate that you want. So that's going to be important. Another method that's used is sodium hydride. We've seen this before. So you can imagine having H minus pick up that proton. This one is a kind of an in-between method, but it's not going to go in reverse because we'll draw the resonance structure one more time. If you're getting tired drawing the resonance structures, I'm just doing it here so you can see it's the same thing over and over. But then we're going to generate H2. So once we generate hydrogen, that's not going to go backwards. So those are three methods of generating an enolate ion. And the key thing is we have a weaker base, and it doesn't have to be ethoxide, it could be methoxide or hydroxide, something with a pK around 16 to 18, or LDA is a very common strong base. Okay.